So good morning. Today we are dealing with our last module, Module 15. It feels great to say that. Module 15 addresses proteins and enzymes. And I hope you did do some reading during your Thanksgiving break. The word proteins comes from the Greek. The term is proteus, and it means, anybody knows what it means? It means first. Okay. These molecules are very, very large, and they perform tremendous number of functions. Proteins are polymers, just like polysaccharides are polymers. And they are composed of, the building blocks of proteins are amino acids. The molecular weight of proteins could be of the order of 64,000. Okay, so we started the course many weeks ago, 15 weeks ago, and our first compound was something like water, molecular weight 18. And we've gone places from there. Okay, our molecules have grown, but now we're talking about the chemistry of life, biochemistry. Some of the functions that proteins have in the body are listed on the screen. One is enzymatic catalysis. What does that mean? Proteins and enzymes. What does it mean that proteins are enzymes? Proteins speed up chemical reactions. That's what it means. So we have a tremendous number of chemical reactions taking place in our body as we speak, and these chemical reactions occur very, very fast because we have enzymes, proteins, that make them happen very, very fast. Hemoglobin is a protein. What does hemoglobin do? It transports oxygen through our entire body. So hemoglobin is a very large protein, again, molecular weight of 64,000. And every cell in our body needs oxygen to develop the reactions. And hemoglobin is the protein that transports oxygen. Hemoglobin has an Fe+2 ion, and the Fe+2 grabs the O2 molecule that we breathe, and the hemoglobin transports it wherever oxygen is needed, and the Fe+2 releases the O2 so that it can be used in the metabolic processes. Also, proteins have a tremendously important function in motion. Okay, so muscle expansion, muscle contraction, that's all done by proteins. Structural components of our body, such as bones, skin, hair, fingernails, that's all proteins. So we can begin to realize why the Greeks call it first. They just have so very many protein functions. Proteins are very important in our immune system. Proteins are also playing a very important role in hormones. Many hormones are proteins, and also in the generation of and transmission of nerve impulses. Okay, so these are some of the very many important functions of proteins. As I said earlier, a protein is a polymer, and it's composed of amino acids. So I am going to, amino acids are the building blocks of protein. So we start from amino acids, and then we will build peptides or proteins by bonding these amino acids. Okay, so very much the same way like we took glucose molecules and we bonded them to form starch, a polysaccharide. We are going to take amino acids, just like taking beads, making a necklace, and linking these amino acids, we will form larger and larger polymers until we get to form a protein. Let me give you the structure of an amino acid. an amino group and a carboxylic acid in the same molecule. So I am going to draw the amino group, and the amino group, remember it had a lone pair, and then you're going to have an alpha carbon with an R group, and an R could be an H, could be a methyl, could be an ethyl, could be, and it has an H, and then it has a carboxylic acid end. So right here we have a structure of an amino acid. This section to the left would be the amino part, and this section to the right would be the carboxylic acid part. So we have a pretty spectacular compound that has both functions of a base. We said that amines are basic molecules, and as well they have functions of an acid. Depending on what R is, R, I said it could be an H, or it could be a methyl, or it could be 20 other things, many different things. R could be nonpolar. So if R is an H or a methyl or an isopropyl, R would be nonpolar. R could also have a polar group or an alcohol group. It could be polar, like it contain an alcohol group. R could contain another amine group. R could contain another carboxylic acid. Okay, so R could have many different structures. And on page 257, you have the 20 amino acids that we have in our body, and it's shading R for you. So if R is an H, the amino acid is called glycine. If R is a CH3, a methyl group, the amino acid is called what? Alanine. Okay, so we have 20 different amino acids in our body, and they all have an amino end, they all have a carboxylic acid, they all have an alpha carbon. Again, this is your alpha carbon. And they all have an R group. And depending on what the structure of R is, whether it's a nonpolar group or whether it's a polar group, whether it's an alcohol or an amine or a carboxylic acid, or maybe it has an aromatic group. Remember benzene rings? Those could be part of R. Or it could have another group, such as an amide group. Or it could have a thiol group. And a thiol group contains sulfur. So if R has something like CH2SH, that's a thiol group, and that's new to us. Okay, so that could be what goes here for R. And if that's what R brings, then that amino acid is called cysteine. Okay? If it has a thiol group but with 3 carbons, then it's methionine. So all the different amino acids are listed on page 257. Look at them. I will ask you to memorize these two, alanine and glycine, because we're going to be constructing dipeptides and polypeptides, so we need to at least know a couple of R groups to function, to draw the structures. Okay, so amino acids may behave as acids because they have a carboxylic acid end. They may behave as base because they have an amino group. They are soluble in water because they have a polar. They have very high melting points, and they migrate in an electric field. So a technique called electrophoresis is used in vitro in the lab to identify the different amino acids that are part of a protein. Okay, let's go ahead and start zeroing in the structure of an amino acid, and it is its properties. I am going to talk about the formation of a zwitterion. This is a German word. Zwitterion means double ion. So I'm going to redraw the amino acid, but I am going to show you that since it has a basic and an acidic character, one end could accept a hydrogen ion, the bases do that, and one other end, the carboxylic acid end, could release this hydrogen ion. So instead of me writing the amino acid like I did it earlier, instead of me writing this structure for the amino acid, in this amino end, NH2, you have a lone pair, so that could accept a hydrogen ion. And this is an acidic hydrogen, so that hydrogen could be released. So this end will change, and this end will change. Zwitterion means double ions. That's what it means in English. So the amino end, instead of just having two H's in the nitrogen, you could have a third one, and then you're going to have a positive charge. The alpha carbon still has the R and the H, and the carboxylic acid could have released that hydrogen ion. So you're going to have a negative end in the carboxylic acid, because that's what carboxylic acids do. They release hydrogen ions. That's what any acid does. And then at this other end, you have a positive charge. So this is a pretty spectacular structure. And this zwitterion exists as a specific pH. So there is a specific pH called the isoelectric point, in which both the negative and the positive charge in the amino acid exists. Okay, so again, this H, that's an acidic H, that could be released, and when it does that, you end up with a negative charge there, and that double dots there, that's lone pair of electrons, could accept that hydrogen ions, and when that hydrogen ion is accepted at that end, a positive charge ends in the amino. Okay, so every amino acid has its own pH. If I start with a zwitterion, like this one, and I lower the pH, okay, so let's say that I am dealing with a specific amino acid. It could be glycine, it could be alanine, it could be cysteine, methionine, any of the listed amino acids in page 257, and I lower the pH. At low pH, do I have a lot of H pluses or very little H pluses? A lot of H pluses. So what do you think that happens to the structure of this zwitterion if I lower the pH? This exists as an isoelectric point. Both charges are there. There's a specific pH for every amino acid where both charges are there. But if I lower the pH from that value, what happens? I am going to protonate the negative. Okay, so at low pH, I have lots of H pluses. And that H plus is going to go where? Plus attracts minus, so these two guys go together. And what is going to happen? I'm going to lose my negative charge. So my amino end, still protonated, still positively charged. Nothing happens to my alpha carbon. Whatever R group I am bringing, it stay there. So that could be a methyl, that could be an H, that could be 20 different things. But this carboxylic acid end is no longer negatively charged. I protonated it. So what charge at low pH, where lots of hydrogen ions are present in my medium, what charge is my? Positive. It has a positive charge. Okay, so it's easy to remember. If I have lots of H pluses, because I have a low pH, my amino acid turns as a positive ion. If I have very high pH or higher than its isoelectric point at high pH, what's going to happen? I have very little OH, very little H plus, lots of OH minuses. Okay, so at high pH, I have lots of hydroxides in my medium, right? Basic pH. And what's going to happen? Is a negative going to react with a negative? No, they repel each other. So the negative is going to go where? Where the positive is, and it is going to remove that hydrogen ion from there, forming HOH, or what? Water. So at high pH, I'm really removing water. And what am I going to be left with? The N no longer have a positive charge. It has the lone pair again. The alpha carbon doesn't change. And the carboxylic acid is negatively charged. So it isn't. So my amino acid at high pH, at higher pH than the isoelectric point, would be what? Negatively charged. Are we okay with that? Okay, so I want you as homework to do problem 2, which tells you to draw the structures of this bitter ion for glycine. So what do you do for glycine? Glycine, for H, you put an, for R, you put an H. And I want you to do this bitter ion for alanine. So for R, you put a CH3. And then tell me what happens when you have a lower and a higher pH for these amino acids than their respective isoelectric points. Okay, so homework problem 2 on page 259. We okay so far? Ready to start linking amino acids? Ready to start forming peptides? Okay, so I am going to begin to form peptides. And first we're going to do a dipeptide, and then we are going to do a tripeptide, and then we're going to continue and get the picture to form a polypeptide, similar to what we did in the carbohydrate chapter, forming a disaccharide or a polysaccharide. Okay, so we start with formation of a dipeptide. I'm going to have amino acid number 1 and amino acid number 2, and I am going to form a dipeptide. Okay, I am going to form a dipeptide, and I'm going to write it like this: AA1 bond AA2. And that bond right there is a peptide bond. We used to call that an amide bond in module 13. Okay, for amino acid number 1, I would like for you to draw alanine. Draw alanine for amino acid number 1, and for amino acid number 2, I want you to draw glycine. So we are going to form alagly. By the way, alagly and glyala are different. Alagly will have a different structure, and we'll see why. Okay, go. Amino acid number 1 is alanine. What do we draw first? N, couple H's, my alpha carbon with an H, and if it's alanine, what do I have? SCH3. Very good. And then I have my double bond O, single bond OH. Are we okay with alanine? And now I am going to draw glycine, and I'm going to draw glycine in a different color. You can use pen and pencil if you don't have two different colors. So how do I draw glycine? I still have my N with my lone pair, my amino end, my alpha carbon, and I have an H and another H. And I have my double bond O, single bond OH. So by now we're comfortable with amines, carboxylic acids, we're comfortable with our organic chemistry, and I am going to dehydrate. What does dehydration means? I remove water. So I am going to form a dipeptide, and this is a dehydration. So when I remove that, is this the very first amino end going to change? Nope. Nothing happens there, so that lone pair is still there. My alanine still has my methyl. Then I'm going to have my carbonyl, and that carbonyl is bonded to what? The N, and that N was red. So I am going to keep that N that lost one of the H's, but still has the alpha carbon with 2 H's and my. So this right here, I used to call it an amide bond, and now I'm going to call it a peptide bond. Okay, so this used to be called amide, and now I'm going to call it a peptide. So how many, this is a dipeptide. How many amide bonds do I have in a dipeptide? I hear 2 and I hear 1. Let's make up our minds. I know it's early, but let's pretend we're awake. How many peptide bonds do I have in a dipeptide? 1 peptide bond in a dipeptide. This right here, that I have CH3, we got to erase that 3 there. This is ala-gly. Okay, so when the molecules get larger in biochemistry, we just use diagrams. In glyala, I would have had an H here and a CH3 here. So there would have been a totally different deal. Glyala is different than, okay, so go ahead and do the same thing for homework and draw, instead of ala-gly, draw glyala and form another peptide. Okay, let's go ahead and form a tripeptide. We form a dipeptide, now I'm here. I'm forming a tripeptide. So I'm going to get this ala-gly tripeptide. I'm going to get ala-gly, and I'm going to add another ala. So what am I going to get? Ala-gly-ala. Okay? Okay, so just memorize a couple of R groups. Just H would be the R group for glycine. Methyl would be the R group for alanine. So we can do this. So I'm going to rewrite the dipeptide that I had. This was ala-gly. So I'm going to start with ala-gly, and I'm going to add another ala to it. Are you with me so far? Yeah. Okay, so I'm going to condense this end because nothing's going to happen in there. And this alpha carbon still has the H and the methyl because it's alanine. And then this carbonyl group no longer has an OH. It's no longer carboxylic acid. It had an amide bond, and this is an NH, and my alpha carbon now has an H and an H because it's gly. And I would draw double bond O, single bond OH, and I am going to now add another ala, and ala is going to be blue again. So it's an H, and I'll spell out the bonds because I am going to dehydrate once more, and my alpha carbon has an H and a methyl, and my carboxylic acid group is still there. Are we okay? And when I dehydrate, what happens? Another water is coming out. So it's another dehydration because I am forming a tripeptide. And this is what I have. I have my NH2 with my N, with my alpha carbon with my methyl, my amide bond, and let's keep it in 2 colors. And now I have glycine, so my R group is an H. And this double bond O is going to be single bond what? Alanine. So I'm going to go back here to my amine group. And my alpha carbon has an H and a CH3. And I think you get the picture of what's happening. And I have a free carboxylic acid group. Okay, so this is ala, gly, ala. Are we okay there? This is a tripeptide. So we formed a tripeptide. How many peptide bonds in a tripeptide? 2 peptide bonds in a tripeptide. Where are they? This is 1 peptide bond, and that's another peptide bond. So I have a C double bond O single bond N, H bonded to more carbons, and so on. So we can see that if we continue to do this, it's like if we're stringing pearls in a pearl necklace, 1 pearl at a time, the pearls being the amino acids, and we're linking them, we are going to be able to have a very long polymer, and this polymer would be, continue to do this, tripeptide plus another amino acid plus another amino acid. You form a what? A polypeptide. Okay, so if you have more than 50 amino acids, you've got a protein. Okay, so whenever you have 50 amino acids bonded together, a protein has been formed. Okay, so proteins are polymers, and the building blocks, the monomers, are amino acids. Questions so far? Again, for homework, do problem 3. Draw the structures for ala. And again, when you're looking at the homework, look at the page where all the amino acids are listed in page 257. So if they're talking about phenylalanine, find out what phenylalanine brings, or valine or whatever. So look at that chart in order for you to know what R is. I just need for you to know glycine and alanine. Okay. Once I have a protein, because I have more than 50 amino acids bonded together, and if I have 50 amino acids, I will have 49 peptide bonds in there. I have constructed what's called the primary structure of the protein. Okay, so I can talk about a protein, and if I call roll the sequence of amino acids of the protein, what I am describing is its primary structure. For example, insulin is a protein. Insulin consists of 51 amino acids. Amino acid number 8, 9, and 10 in human insulin is different than amino acid 8, 9, and 10 in sheep insulin. Okay, so whether you have an animal or a human hormone, insulin, they may not be identical. Like in human insulin, you have threonine, then you have serine, and then you have isoleucine. In sheep, you have alanine, and you have glycine, and you have valine. Many people that are diabetic, many people that have malfunctions of blood metabolism need insulin, and if human insulin is not available, you could substitute it by another type of insulin, and it's okay. It still works the same way. So we can switch one amino acid by another and nothing major happens. So we can change the primary structure, change a few amino acids in a total list of 51, and still the protein acts in the same way that the human protein did. But some other cases, in the case of hemoglobin abbreviated HB, normal human hemoglobin, amino acid number 6 is glutamine. And if you change amino acid number 6 in hemoglobin, and hemoglobin has a total of 574 amino acids. Okay, molecular weight 64,000. So we're talking about a big polymer. Very important one. 574, you're switching one, amino acid number 6. And instead of having glutamine, you put valine. That gives you sickle cell. And that is a condition that can be lethal. So you change one amino acid in a total of 574, and your protein doesn't work. It doesn't do what it's supposed to be doing, which is transport oxygen throughout. And it can cause death. Okay, so the primary structure can be elucidated by just calling roll what's amino acid number 1, what's amino acid number 2, 3, 4, 5, in a series of as many as may it have. And sometimes one change in an amino acid does nothing, and sometimes it's the difference between life and death. Okay, so these proteins are so complex that it have many different structures, and we are just referring to the very first of many, the primary structure. Are we okay so far? Besides the primary structure, okay, so I'm really talking about the relationship between structure and function of a protein. You change the structure, the primary structure, you change one amino acid, and the function's no longer operative. Sometimes it's not the primary structure that's changed, but in proteins, besides the primary structure, you're going to have a secondary structure, a tertiary structure, and some proteins are so complex that they even may have a quaternary structure. Let's see what I mean by this. Okay, so the primary structure is just a sequence of amino acids. First I have glycine, then I have valine, then I have alanine or whatever. Then as these amino acids bond and form peptide bonds, and they link and form the primary structure, they begin to curl. Pretty similar to this cord for the phone and the wall right here. Okay, so if you have a helical structure, just like a phone cord, pretty soon we're not going to know what those are. Everybody's wireless. Amino acid number 1 is bonded to amino acid number 2, which is bonded to amino acid number 3. You are going to have hydrogen bonds among them. And they're going to form like little helix. That is one of the secondary structures. So I am going to show you what a secondary structure for an amino acid looks like. And again, this shaded is an amino acid. And then you turn it and it's another amino acid. And you turn it again and it's another amino acid. And that forms an alpha helical structure. And it's held together by hydrogen bonding. Okay, so it's H hydrogen bonding. Where do these hydrogen bondings come? Well, in amino end, in one end of the amino acid, you have an H. And then couple of amino acids down the line, you're going to have a carbonyl group. And they, slightly positive hydrogen and the slightly negative carbonyl, the oxygen, will attract each other, plus attracts minus, and they will bond. Okay, so you are going to form alpha helical groups. Silk is a protein, and it has a different type of secondary structure. It forms intermolecular hydrogen bonding between two proteins. Intermolecular hydrogen bonding between two proteins. So you have a protein and a second protein. And the carboxylic acid in the first protein is to the right. And the second protein, the amino end, is to the right. So they're still going to hydrogen bond, and it's the amino group of the first protein and the carbonyl group of the second one. So silk has its own type of secondary structure, and they form what's called pleated sheets. So an alpha helix or a beta pleated are both part of the secondary structure of proteins. Okay, so these molecules are getting so complex that they begin to fold. Are we okay so far? Okay. Besides the primary structure and the secondary structure, proteins have a what? Tertiary structure. Now I want you to imagine that telephone cord, but that telephone cord begins to ravel. And that's something that, okay, so if I get this telephone cord and I go like this, that's no longer the same structure. I am going to have amino acid number 1, peptide bond, amino acid number 2, amino acid number 1, peptide bond, amino acid number 2, peptide bond, amino acid number 3, and I'm going to have a hydrogen bond with amino acid number 4, and so on. And now, maybe in here, I have a cysteine, which contain a thiol bond. We said that earlier. Sulfur. And then maybe 50 amino acids later, I have another cysteine. And I am going to form bonds in there. So they're going to lock and form a disulfide bond. Okay, that is a disulfide linkage. This could be a cysteine, and this could be a cysteine. And they could be very far apart. You can form more hydrogen bonds. Anytime an amino end of an amino acid. Okay, so the tertiary structure have many different types of bonds. Disulfide linkage is one of them. Hydrogen bond is the second one of them. You have a carbonyl in one amino acid and an amino end in another amino acid. Those are hydrogen bonds. You could have a salt bridge, because these amino acids have their own Zwitterion structures, and at specific pH, one of these Zwitterion may be forming a protonated amino end, or maybe another one would have a negative end in the carboxylic acid, and those are ionic bonds. Salt bridges are ionic bonds, and ionic interactions are very, very important in tertiary structure of proteins. Ionic bonds, and they are going to keep that region of the protein bonded together. And finally, a fourth type of bond that triggers the tertiary structure would be hydrophobic interactions. Non-polar groups, like benzene groups in phenylalanine, could be attracting each other. So in here you could have a phenyl, and in here you could have another phenyl, and they are going to love each other because non-polar attracts non-polar, and that section of the protein is going to keep bonded in there. So in order for a protein to function, the amino acids have to be in the proper sequence. That's the primary structure. Then they're going to form your alpha helix. They're going to coil with hydrogen bonds. They've got to have that structure. And then that whole sequence, I may have a plus and a minus with ionic bridges, hydrophobic interactions maybe in here, hydrogen bonds maybe in here. All of those bonds got to be in place. And this looks like a crazy structure, but the protein will never function unless every one of these bonds is intact. Okay, so our molecules are getting so complex that you have now primary, secondary, tertiary structures in order for the function of the protein to be operative, in order for it to happen. Okay, so whatever the protein is going to be doing, muscle expansion or contraction, whether it's a nerve impulses, whether it's a hormone, whether it's hemoglobin transporting oxygen, whatever it is, all these hydrogen bonds, hydrophobic interactions, salt bridges, they all need to be identical. And some proteins are so complex, like hemoglobin, and then this is my own drawing, so I apologize for the art. You're going to have, this is hemoglobin, 4 chains of protein. This is a chain, and this is another chain, and those are alpha chains, and the darker ones are beta. So you have 4 chains, and each one of those chains have its primary, secondary, and tertiary structure with their hydrophobic interactions and their ionic salt bridges in place in order for them to function. And once they function, then hemoglobin can go ahead. You have 2 alphas and 2 beta chains, and it will go ahead and transport oxygen throughout your body. So as you're breathing every second of the day, this has to be, every bond has to be just perfectly so. You unravel any of these, the function, in this case would be transport, would no longer happen. Okay, so now that we know about covalent bonds and ionic bonds, we can begin to see how important these are in life, in our everyday breathing. Okay, things that we take totally for granted. Let's see what happens if we, on page 264, by the way, you have a wonderful picture of the primary, secondary, tertiary, and quaternary structures of the protein, all in one diagram. Let's see what happens when denaturation takes place. Denaturation of proteins. I studied, after my PhD, I was getting a postdoc at med school, and I was working in biochemistry. And we used to work with proteins, and we had to work in this huge rooms that were refrigerated, like a huge refrigerator. And we would work with proteins, very large molecules. And sometimes, if you shook them too much, you're disrupting these bonds. Or if you breathed on them a little bit too close, you are going to disrupt this primary or secondary, not the primary, but the secondary and the tertiary and the quaternary structure by far could be affected. Okay? And the proteins would be denatured. So there goes 3 months of work down the line. So proteins are very delicate, very important, but very, very intricate. And they could have a specific structure, and you can heat it. Triangle on the arrow means heat, and it uncurls. It looks like a frustrated spaghetti here. And once it unravels, once you disrupted that ionic bond or that non-polar hydrophobic interaction or the disulfide bonds, whatever function the protein was about to do, it doesn't go back. Okay, so heat is one denaturation agent. Okay, denaturation agents. Number one is heat. You can denature a protein, and sometimes you can denature a protein by just heating it a little bit, and if it's just you just heated it at maybe a degree or two, it unraveled, but maybe if you bring it back down to the original temperature, denaturation could be reversible. But if eggs are a protein, and when you fry an egg, you're denaturing the protein. And after you fry an egg, the protein no longer looks the same, does it? And you can cool it all you want after you fry it. And it is going to be totally irreversible. Okay, so sometimes denaturation is reversible if you can bring it back to its original structure and the function will be restored. But sometimes denaturation is irreversible. Thank you. Another denaturation agent would be what? Who read? Shaking, yes, shaking would be one. So if you shake it hard enough, you are going to break those bonds. You are going to disrupt them. When I say heat, by the way, I forgot to say, but what is the normal temperature that a protein would love to be at?
You said it was refrigerated for like a cold, like really cold.
Okay, where are these proteins? Are they in your body? So what is the temperature of your body? Okay, so body temperature is the ideal temperature. And you can, you know, if you take that temperature, and so an egg in a chicken is not 100 degrees. So if you throw it in a frying pan and you're going to throw it in there and you're going to change the temperature, you are going to disrupt all these bondings. All these. Okay? What other denaturation agent? Acids. Yes, we saw that we have a negative end and a positive end, and those could be altered by adding or removing H pluses in your system. So if you add acids or bases, meaning pH changes, you can no longer have a negative charge where it used to be, or no longer have a positive charge where it used to be, just like the zwitterions did. And that could unravel, denature the protein. What else? Alcohols, absolutely. So if you have polar groups and you're adding other polar groups like alcohols, like what? That's why they tell you if you have, like, I don't know, pink eye, get alcohol and denature whatever bacteria may be affecting you. So alcohol will denature, clean, disinfect by killing the protein of bacteria. It will totally unravel it. Alcohol, or when I say alcohol, it could be any other organic solvent. One more. Metals. Metal ions and reducing agents. You ever permed your hair? I used to wear my hair permed. All they do when they perm your hair is protein. Fingernails are protein. Bones are protein. So we're all one big protein molecule. And once you want to change the structure of your hair, you are going to put them in little rods, and you're going to add a reducing agent, and you are going to make your disulfide bonds in a different place. And now your hair is no longer straight, but it's curly. So you can use these in the cosmetic industry. And yes, heavy metals. Like silver, lead, mercury. These will bind to a negative end that you may have in a specific side of the protein, and that will unravel its structure and change the structure. Therefore, the function will be totally affected by it. Okay, so again, denaturation could be reversible or irreversible, and these are the agents that cause it. Do we have any questions so far? Yes.
If the protein has to stay at like 98.6 degrees, why did you work with them on cold?
Okay, it goes 98.6 degrees, but it goes all the way to, there's a range. Okay, yeah. It's just when you heat it. Okay, you can chill it a bit, and you're still safe because you're working with them, so you really want to have a buffer and have it a little lower. Okay, but it's when you go from 98 to 100 degrees, then you're out of luck. Okay, like a fried egg. You can cool it all you want. You can boil an egg, and after it's been denatured, it's not going to go back to its original state. Any other questions? Okay, so I'm going to leave it up to here. Have a great day, and I'll see you next time.